Today we are going to start this subject that is called Theory of Computation. Okay, and briefly let's have an introduction about this and the weightage of this particular subjects. So in GATE examination, if you say though, let's say by law of an average, then there will be 4 to 5 questions from this particular subject. Okay, 4 to 5 questions, and let's say 8 to 10 marks. Let's say 7 to 10 marks. Okay, and but it has been seen from previous few years that there is some weightage given to this question, but still I would say that there will be the question around 4 to 5 questions, and marks will be around 7 to 8 marks. Now this particular subject is a scoring subject. Okay, scoring subject, and if you really can go through the concept well, and you can understand all this concept or practice this subject, then I think you can fetch all of the marks. Okay, most of the concepts are not very difficult, but it required practice. Okay, so more you practice about this particular subject, theory of computation, more comfortable you will be, and you will gain confidence. Okay, you will gain confidence by practicing more and more to this subject, theory of computation. What this subject is about, okay, briefly let me introduce this thing also, what basically this subject is about. So it's a theoretical foundation, it's a mathematical foundation. Okay, it's a mathematical foundation. Mathematical foundation of computation. Okay, so what we are going to learn here is a theoretical aspect or mathematical aspect of computation. Okay, computation, in a sense, what we are talking about is problem solving. Okay, what is a computation? There is a problem and problem solving. Okay, so theoretical or mathematical definition: problem solving, computation, problem solving, and problem itself. Okay, so now you can understand that it's a theory for what? Theoretical, how you define a problem. Okay, theory is theoretical subject, how you define a problem, and what is basically a problem solving. Theory about problem and problem solving. So there are 3 different branches of this particular subject. There are 3 different branches, 3 different aspects of this theory of computation, and this is basically the syllabus only, that there are 3 aspects. The first one is called Automata Theory. Second part is called Complexity Theory. Complexity Theory. And third part is called Computability Theory. So there are 3 different aspects of this subject that as I mentioned, that theory of computation, how you define the 3 different branches of theory of computation in the 3 different ways: automata theory, complexity theory, and computability theory. Okay. Now before 2015, we had all the 3 in our syllabus. We had automata theory, we had the complexity theory, we had the computability theory. Now this is not in your course now, right now. Okay, complexity theory is not part of our syllabus. It has been removed from 2015 onwards, and now we are only left with automata theory and computability theory. Okay, terms are important. Okay, terms are important. So what basically a computability theory is? Basically this computability theory, I am introducing a new term. Later we'll come to this definition. I am using a term decidable. Okay, decidable or undecidable. Okay, so I'm just introducing the term, this term, that or let's say just an introduction. What is computability theory is about? It's about decidable and undecidable problems. Okay, so again later we'll talk about and we'll discuss this particular term, what is decidable, what is undecidable, but briefly. Okay, now this is about automata theory. We don't have this part in our course, and computability theory. Now the first part is your automata theory. Let me briefly also describe this thing. What is automata theory? Okay. Now automata theory is about machine models. Okay, machine models, and of course mathematical machine models for computation. Okay, machine models for the computation. Automata theory, what are the different machine models that are available for the computation purpose? As I told you that what we are learning is theory of computation. So how this computation is being done, and that is a machine model, theoretical model, mathematical model, machine models for computation. So we have three very standard machine models for the computation. Finite state machine, push down automata, and third one is Turing machine. Okay, so there are three different machine models for the computation, standard machine models for the computation: finite state machine, push down automata, and Turing machine. Now, each machine model we are going to learn in different aspects. Okay, each machine model will be learned in different aspect, and we will keep on doing this thing for FSM, PDA, and Turing machine. So these aspects are design. Okay, design of machines. These are the aspects that we are going to focus, that how to design FSM, how to design PDA, how to design Turing machine. Okay. Second is that what type of the computation they perform. Again, I'm introducing a new term in this case. Don't worry, later every definition will be covered properly. What the main heading is what computation, what problem it solves, what problem solved by FSM, PDA, Turing machine, what type of the problem they solve. And I'm using a term, what language. Okay, this is the first time I'm using the term, what language accepted. Okay, language accepted by machine. Okay, do not hurry, just write it down as an heading. What is a term that language is the first time I'm using the language term. I'll just describe after a short while. Okay, so what problem, okay, say language accepted by the machine, or I'm writing here problem solved by the machine. Problem solved by machine. Okay, so what language accepted by the machine, and that is equivalent to problem solved by the machine. Okay, then we talk about for each machine closure properties, closure properties of language. Okay, again it's a new term. I'll explain. Okay, I'll explain what is a closure property. It's an introductory part, and after a while we'll go here. Closure properties of the language. Next is decidable properties of the language. Okay, decidable properties of the language. Okay, so okay, so I have introduced a term, few terms I have introduced. You must be worried what are these terms. We'll cover it. Okay, we'll cover it. But each machine will going to have some aspect, or you can say this is the structure of the course that what we are going to do. FSM. What we're going to do in FSM? We'll design the machine. We'll see what type of the language it accepts. We'll see what is the closure property for that language, and we will see that what is the decidable property for this language. So these are the main aspects by which what we are going to learn, what we are going through in this course for FSM, PDA, and Turing machine. So same thing will be for push down automata, same thing will be for Turing machine. Okay, so this is our structure of our course. Okay, this is how we are going to progress in this entire theory of computation classes. Okay, so okay, this is again introductory part. This is the structure or syllabus of our course. Okay, now this entire I started with automata theory because what we are going to learn it first, and then we later will go to the computability theory. So I'm not describing it here. The entire part, the main part is basically 80-20%, 80% automata theory, 20% computability theory. So first we are going to complete automata theory. We will reach down up to Turing machine, and then we'll take up this computability theory part. Okay. So again, a few more basic fundamental things that you might be aware of. This whole subject, theory of computation, okay, this whole theory of computation is nothing but it is equivalent to your set theory. Okay, now this particular part is a prerequisite. Okay, this particular part is a prerequisite for this subject, that you must have a profound, or let's say very clear idea about what basically a set theory is. Set theory and its operations. Okay, so I'll just go through with a few of them, some of them. Okay, so some of this operation, and you can just also revise the certain aspect of it. Okay, so I'm defining a set. Okay, I'm not going to very basic detail what is a set. Okay, ordered collection. So I'm writing a sets here. Okay, and this is how we are going to denote. U is my universal set. Okay, now it is consists of few elements, 1 2 3, let's say 4 5 6. I'm not teaching you set theory, I'm just revising few concept that I required later when we are going to learn theory of computation. Okay, now this is my universal set, and let's say this is S1, that is consist of 1 2 3. Okay, and this is your S2, which is consist of let's say 3 4 5. Okay, 3 4 5 6. Okay, so I'm more interested in basically this terms or the English translation of it. So very basic operations are union. Okay, so results, you know, this is a very trivial question as an engineering student, that I ask you what is S1 union S2. I'm really not interested in S1 union S2. What I'm more interested in, that what is the meaning of S1 union S2. Okay, so union is described by union is equal to S1 union S2. Well, I'm really not interested what is union of this S1 and S2 set, but basically what is the description of S1 union S2. Okay, now S1 union S2 is all X. Okay, all X such that X is the element of S1, or okay, or X is the element of S2. Okay, now this is I'm really interested in, that how you describe a union thing. So union is that all element X such that either element X is the element of S1 or X is the element of S2. Now what you have to understand, this connective that we are using in this case is OR. Okay, and how OR works, now this is again a very trivial thing, 0 0 0 1 1 0 1 1. So 0 1 1 1. So element will be part of union when it is part of, let's say, S1 and S2, when it is not part of S1 but part of S2, part of S2 but not part of S1 but not part of S2. It is participate, or it's an element of both. Okay, so the connective here in this case is OR. Okay, result, you can find out what is the result. Intersection. Okay, intersection notation, you know, S1 intersection S2. Okay, and what is this? X, all element X. Okay, that we say common element, and how we describe this situation is that X is element of S1 and, okay, and X is element of S2. Okay, so this is your basic very trivial operation, AND operation, 0 0 0 1 1 0 1 1. Answer is 0 0 0 0, and last one is, sorry, 1. So there are really, you know, few connectives which I'm very interested in this case. The first one is basically an OR, which is nothing but a union thing, and the second one is AND, which is nothing but the intersection. Okay, so it will be part of this S1 intersection S2 is a set of all element X such that X is the element of S1 and X is the element of S2. So you focus on this OR is union and is intersection. Okay. Okay, cardinality. Okay, cardinality. Okay, now cardinality, or let's say intersection S1 union S2 complement. Let's say complement. Okay, complement. Okay, so S1, let's say S1 complement is what? All x such that x is not element of S1. Okay, now if x is not element of S1, x is not element of S1, then what is it is element of? So we always need what we need always is a universal set. Okay, we always talk about a universal set. So in this case, this is my universal set. Okay, and we are interested in x. We are interested in all x such that x is not element of S1. So in this case, x is not element of x is 1, 2, 3. Then definitely 4, 5, 6 is basically the element of S1 complement. So basically that the term that we are using in this case is okay. X is not, okay, not element of S1. Okay, so in this case the connective that we are using in this case is not. So 0 becomes 1, 1 becomes 0. Okay, so not property is very simple, 0 to 1, 1 to 0. Okay, so this is your basic three operation: cardinality, union, intersection, and complement. Cardinality is not, we don't need a definition, but cardinality is basically notation wise. This is written in this way: S1 modulus of, like this is the notation for cardinality. Okay, cardinality. And in this case, the number of element present, okay, it's a natural number, maybe natural number. Cardinality S1 is equal to 3. So the number of element present in the set is basically nothing but the cardinality. But in this case, this is nothing but represented by in this way, that S1, and this is the symbol, this is the notation for it. Okay, so these are very basic thing. Okay, I hope you are aware of union or intersection, and not is basically for a complement. Okay. Okay, let's proceed few more things about this set theory. Okay, so this is my like universal set: 1, 2, 3, 4, 5, 6, and S1 was equal to 1, 2, 3, and S2 was a set which is equal to 3, 4, 5, and 6. Okay. Now subsets. Okay, subsets. So okay, subset. Okay, and proper subset. Okay, so subset and proper subset. Now I'm not interested in the definition. I'll just give you some example and few things that you need to remember about subset and proper subset. Now subset can be equal. Okay, this subset thing can be equal. Notation. Okay, now this can be equal. Subset can be equal. Okay, it can be equal. So you can claim that 1, 2, 3 is a subset of S1. This is a very much valid notation. It's a true proposition that it's true. Okay, this proposition is true. 1, 2, 3 is a subset of S1. Also you can claim, okay, that 1, 2 is a subset of S1. This is also true. Okay, 1, 2, 3 is a subset of this. Both statements are true. Okay, this what you cannot claim is 1, 2, 3 is a subset of, proper subset of S1. Now this is false. Okay, this is false. You have to, when you say proper subset, and you can see this thing as equal, and this is only used as a proper subset. Proper subset should exclude at least one element. Okay, so you cannot claim this situation. This is false. This is particularly 1, 2 is a proper subset of S1. Now this is true. Okay, so the only idea that only concept that take away from this particular Subset and proper subset is that in subset can be equal. Okay, and proper subset, when you talk about, you have to exclude at least one element. Okay, you have to exclude at least one element, and then we can call it as a proper subset. Okay, so that is a very small thing. I think you might have recollected if you are done with this set theory part. Subset and proper subset. Okay, we'll use it. Okay, you might be wondering why we are learning this set theory unnecessarily. Okay, no, there is a reason for it, and later you will understand that we really required this per part before we go to theory of computation. Okay, now power set. Okay, power set. Power set. Okay, so this power set definition is what? Definition is very simple. Set of all subset. Okay, set of all subset of a given set. Okay, of a given set. Okay, set of all subset of a given set is basically called as a power set. So if your element is 1, 2, 3, okay, let's say, okay, now notation wise sometime it is written as P row of S1, okay, row. Okay, it's not P, it's a row of S1, and that is a few standard book used this as a notation. Okay, proper subset, set of all subset. Okay, so my set is 1, 2, 3, okay, and I want all the subsets, all the subset of this set 1, 2, 3. Notations are important in set theory. Okay, now these are the set of all subset, and this is S1. Okay, now in this case, now what you can do of 1, 2, 3, you can take no element from that. Don't select any element. Okay, and that gives you your first notation of the set theory, and that definitions you must be very clear with you to understand this, that what is this is a null set. Okay, and the symbolic notation for the null set or empty set is phi. Okay, symbolic notation for this null set or empty set is phi. So what is a phi? Okay, this is the first time I'm introducing this particular notation, phi. Phi is an empty set. Okay, what is phi? Phi is an empty set. Okay, phi is empty set. Okay, okay, this is the most important. Okay, now this will come again and again. What is phi? Phi is nothing but a set, and it's an empty set. A set consists of no element. Okay, a set consists of no element. So phi, then what? Then let's say 1 single element, 2 single element, then 2 element, 1, 2, 2, 3, 3, 1, and 1, 2, 3. Okay, so this is the subset, all subset possible over S1. Okay, what is this? This is n. N is the cardinality. Okay, what is n? N is, suppose S1 cardinality is equal to n. So what is this? This is nothing but NC0. Okay, and what is this? Out of this 3 element, take common NC1. Okay, what is this part? What is this part is nothing but take 2 element common, NC2. Okay, number of space we can select 2 element, and this is nothing but NC3 or NC, let's say common generalized notation, NCN. Okay, so this is how you can select the element out of a given set from S1, okay, which is consist of n element, cardinality of n element. You can select NC0, NC1, NC2, and up to all element. So consist of no element, 1 element, 2 element, all element. Okay, and this sum is equal to, everyone is aware of, 2 to the power n. Okay, NC0 is a very common series, NC0, NC1, NC2 up to NCN. This is very common series, and this is equal to nothing but 2 to the power n. So if S1, cardinality of a set S1 is equal to n, cardinality of power set of S1, okay, remember the notation, that is 2 to the power n. Okay, So very small thing, very simple thing. What is a subset? How many subsets are possible with n element? 2 to the power n subsets are possible for a set consist of n element. Okay, so this is nothing but number of subsets possible. Okay, number of subsets possible. Number of subsets possible. Okay, so small thing you might be aware of. Okay, take it as a revision for it. Okay, power set, number of subset 2 to the power n. Okay, fine. So I hope I am clear with this. Okay, let's proceed further. Okay, so last thing is symmetric difference. Okay, set difference, symmetric difference, S1 minus S2. Okay, so S1 minus S2, I didn't introduce it there, but let's say S1 as my S1 minus S2. Okay, S1 minus S2, symmetric difference. Okay, now symmetric difference is a definition. Okay, let's just have a definition. All x, okay, we are interested in all x such that, okay, x is element of S1 and, okay, and x is not element of S2. Okay, now this is the definition of symmetric difference, that we are interested in those elements which are exclusively, okay, which are only element of S1 and it is not element of S2. So what we are interested in this, that you just translate this notation into symbolic notation. S1 minus S2, we are interested in all element of S1 and it's for intersection. Okay, and is for intersection and it is not element of S2. So S1 intersection S2 complement. In this case we are having this and thing, and is equal to intersection, and I already told you the complemented part. So that is nothing but S2 complement. S1 minus S2, okay, S1 minus S2, okay, S1 minus S2 is equal to S1 intersection S2 complement, that it is part of S1 and it should not be part of S2. So you can now find out that exclusively only for S1. So 3 is the common element. Okay, so 1 and 2 will satisfy this condition, that 1 and 2 will be part of S1 and 1 and 2 is not part of S2. So S1 minus S2 will be equal to 1 and 2. 3 will dissatisfy this condition. So both the condition must be true. Okay. Okay, so this is S1 minus S2 is a symmetric difference, and this you have to remember that this is an equivalent form of it, S1 intersection S2 complement. Okay, so equivalence problem. Okay, now okay. So given two set, now definition is important. Okay, so given two sets S1 and S2, okay, S1 and S2 is S1 is equal to S2. Okay, so this is called basically a equivalence problem, that two sets are equal or not. Okay, we want this thing too. So how to find out whether these two sets are equal or not? Okay, so I'll give you two set. So or a sub problem can be like is S1 is a subset of S2 or not? Okay, S1 is a subset of S2 or not? Okay, so now that is how we can get to one problem to another problem. Okay, if S1 is a subset of S2, okay, if every element of S1 is present in every element of S2, so understand the context why we are reading this thing, why I'm asking this question, because that is something related with this. Okay, so if S1 is a subset of S2, okay, now I'm only answering the first part. If S1 is a subset of S2, then S1 minus S2, okay, this operation if you perform S1 minus S2 will result in phi. Okay, what is phi? Phi is a empty set. Okay, what is phi? Phi is a empty set. Okay, this way. So this will prove this will enough to conclude that S1 is a subset of, this implies that S1 is, if it is equal to phi, if S1 minus S2 is phi, this implies that S1 is a subset of S2. Okay, but that is not that will not prove that S1 is equal to S2. Okay, that will not prove the second part of it, that they are equal. It is only saying the one part, that S1 is a subset of S2. What I need to also see, okay, what I need to see, S2 is also subset of S1. Okay, now both should be true. S2 should be also S2. Okay, should be a subset of S1. This should also be true. So if S1 minus S2 is equal to phi, the empty set, then for equality I have to check one more thing, that S2 minus S1 should also be equal to phi. Okay, so both should be phi and their union, okay, their union must be equal to phi. Okay, union, intersection may be phi. Okay, in intersection there are some element present here, there are some element, they are not common. Okay, so it can be phi, their union should be phi. Okay, so two sets S1 and S2, is S1 is equal to S2 will depend on two things. S1 is a subset of S2, S2 is a subset of S1, and how can we check this thing? By very simple, using the symmetric difference, S1 minus S2 and S2 minus S1, and their union should be equal to phi. Okay, so let me summarize this, that the two sets are equal. Okay, it depends on this condition, two condition, and if these two sets are equal, then okay, S1 minus S2, okay, union S2 minus S1 should be equal to phi. Okay, S1 intersection S2 complement union S2 intersection S1 complement, this should be equal to phi. Okay, so this is how we check two sets are equal, two given sets are equal, S1 minus S2 union S2 minus S1, this should result, this should be an empty set. Okay. Okay, so I think we are done with all basic set operation we have done, we have revised it. I'm more interested in OR and this NOT thing. Okay, and power set, we have also concluded that power set is consist of 2 to the power n element. One of the more operation that may encounter, minus thing is very popular in theory of computation among questions, that you will get minus again and again, and we have seen what is a minus, S1 minus S2. Okay, that can be described as S1 intersection S2 complement. And you want to check equivalence, that is certainly this problem only, okay, related with this problem. And what we are checking is subset property. S1 is a subset of S2, union S2 is a subset of S2, S2 is a subset of S1, this should be equal to phi. Okay, so I hope I'm clear here. Okay, you can post your doubt if you have any. Okay, so let's proceed. Okay, quantification. Okay, now again, why you'll be wondering why I say all this thing. Okay, there is a reason for it, why I explain these small things. Quantification, this is also important. Quantification. Okay, and you know the two ways we can do the quantification is existential quantifier and universal quantifier. Okay, so this is also important in theory of computation, that why it is important. Okay, again, as the course will progress, you'll understand why it is important. But the most common term that you will be getting going through the GATE question that will be all string, huh? Okay, all string. Okay, now this is the most common term that you will be getting in the GATE question related with theory of computation. All string. Okay, now all string. Now this quantification, this when we say all string, this quantification is a universal quantification. Okay, universal quantification. Okay, so in this case, if you're talking about some string, okay, now existential quantification is nothing but there are few string, few, let's say few items, few terms satisfy the property. Okay, so you can only have a few terms satisfy the property, satisfies the property. Okay. Okay, now for example, okay, natural number. Okay, so let's say n is a natural number, and 1, 2, 3, okay, 4, and so on. Now all natural numbers, okay, all natural numbers, or two proposition I'm writing, all natural numbers divisible, okay, divisible by, let's say, 2. Okay, now what I am doing here in this case, the statement, the proposition, what this proposition is doing, that it is doing a quantification, and it is trying to do quantification is universal. It is commenting that all natural numbers are divisible by 2. Now you like this proposition is false. Okay, this proposition is false. Why it is false? This is false because, how to prove it as a false is by contradiction. Okay. Okay, so I can go for the contradiction, and you have to find only one contradiction. Okay, if you want to disprove something, if you want to disprove a universal quantification, you want to say it's false, then you need only one contradiction. Okay, so find an element that dissatisfies the property. All elements satisfy the property. Okay, some elements satisfy the property. This is commenting all elements. Okay, so find a natural number, all natural number divisible by 2. You have to give a contradiction. Okay, so okay, so divisible by 2. So let's say 3 by 2. Okay, now this is a contradiction. The 3 is not divisible by 2. Okay, it's not a perfect divisor. It will result in a fraction part. Okay, so one contradiction. So this proposition is false. Why? Because there exists one contradiction. So if there is a proposition that say all string, and if I find a single string dissatisfying the condition, you can directly remove or say that option from the GATE quotient is false. Okay, so yes, it is somehow related, or somehow closely related with this proposition thing. Okay, it will claim, the statements of the options of GATE quotient will claim that all string, what you have to do is you have to find a contradiction. Okay, like here, all natural number divisible by 2, false. Why? 3 divided by 2. Whereas you will never get any contradiction. Okay, if I say divisible by 1, yes, it is true. Okay, so no contradiction exists. Okay, but you have to learn the logic of disproving something. You have to, because that is how the options are created in this GATE examination. You have to understand and learn how to disprove something. Okay, so that is something related with basically this quantification only, universal quantification and existential quantification. For some it is true. Okay, where for some it is true, you cannot say all. Okay, and if it is true for all, okay, then definitely you will never get any contradiction. Okay? So that is something that will come again and again. Again, you might be feeling that again why it is important. So later, as the course will progress, again you will understand that this existential and universal quantification, that is how options are created actually. Okay? So I hope I'm clear here. Okay, existential for some, universal is for all. More introduction. Okay, then I'll go to this closure property. Okay, closure. Okay, this term I have used when I introduction that we have to read or learn this subject in this particular divisions are there, and one of the division is closure property. Okay, so I can take the same example that I have taken. Let's say natural. Okay, what is the definition? The definition of closure property is very simple. So according to this definition of closure property, that it's about a set. Okay, it's about a set, and the definition is a set has a closure under an operation if performance of that operation on member of the set always produce member of the same set. Okay, so this is the closure properties is different term, and what I am writing is a closure operation. Okay, closure operation. Okay, so a set has a closure under an operation if performance of that operation on the member of the set always produce the member of the same set. Okay, not complicated definition. Okay, but things are very simple. Okay, let's have a natural number n. Okay, so okay, now I'll say natural number. Now this is the proposition again. Okay, natural numbers. Okay, natural numbers are closed under. Okay, closed under addition operation. Okay, addition operation. So what and it's a binary operation. Fine. So natural numbers are closed under addition operation. Now what this statement is saying in this case is that, now go through this. A set is closure under operation if performance of the operation on the member of it. So you take member of it. Okay, you take a member of natural number. You take two member, random member 4 and let's say 6. Okay, and you perform the operation 4 plus 6. Okay, the result should be element of n always. No contradiction. Universal quantification. Okay, so when you comment this natural numbers are closed under addition operation, the quantification here in this case is universal, that for all x and for all x1 plus x2 is element of, okay, element of n natural number. Okay, so yes, always true. Okay, always true that if you have a natural number and you take the two number and you perform addition operation, result will belong to the natural number. Even you can claim this thing for multiplication also. Okay, multiplication also you can claim the same thing, that they are closed under multiplication. You multiply two numbers. But what you cannot claim in this case is natural number proposition again. Natural number, because I am doing quantification, you can say also first order logic, but anyway, true or false. Natural numbers are closed under, okay, closed under subtraction minus operation. Okay, now what we are claiming is for all. You understand the meaning of it, okay, and this is very tricky thing. Later you might be confused with this. So understand the trickiness of this. I am making a statement, I am making a proposition in this case that this closed under subtraction operation. So you can say, you can argue here, yes, 4 minus 1 is equal to 3. 3 is a member of natural number. Okay, you can argue that 10 minus 6 is equal to 4. It's an all our element, all this are resulting in element that belongs to natural number. Okay, so you can argue in this way. But the problem is when it comes to the quantification, it should be true for all. I should not get any contradiction in this case. The moment I'll get the contradiction, then this statement automatically become false. What will become false is universal quantification will become false. I cannot say. I can say some, okay, some natural numbers are closed under subtraction. That is true statement. Okay, some natural numbers I can say, but I can't say all. So I need one contradiction for it, and contradiction can be 6 minus, let's say, 10. And it will result in minus 4. And minus 4 negative numbers are not part of the natural number. Okay, so I cannot when I say closed under, I need strictly, okay, strictly a universal quantification. If you give me an example that, sir, this is the two numbers which are basically resulting in natural number. So based on one or two example, I cannot conclude that they are closed under this subtraction operation. Okay, so the closure operation is for universal quantification, and if I give you a single contradiction, then this statement will become false. Then you cannot quantify universally, you have to say some natural numbers are closed under subtraction. This is true statement. Okay, so but the only point is when we talk about closure property, it will satisfied by all. I don't require a single contradiction over there to say that they are closed under. Okay, if one contradiction is there, statement will become false. Closure property dissatisfied. Closure operation, and that will go and say closure property for the language. Okay, so that is simple closure properties. Okay, so the term that I have used, closure property, I already explained you. Machine models for the computation, I'll come to that. Okay, before we proceed the entire course, this entire course is about languages. Okay, and let's introduce the term language. Okay, so yeah, before I just go to the main topic, let's say I have to complete the basic one, and still we are learning the prerequisite or the basic of theory of computation. Okay, language. Okay, now next one is a language. What you called a language. Okay, so basic unit. Okay, the basic unit of language. Okay, basic unit of language. Before defining language, what you need is equal to, okay, before defining any language, what you need is the basic unit is of language is alphabet. You need an alphabet for it. Okay, now straight away there can be alphabet, English alphabet, Hindi alphabet, Bengali alphabet, Telugu alphabets. Okay, so there are alphabets, symbols, basic symbols. Okay, the symbols. Okay, so the basic unit of the language is your alphabet. Okay, and now comes the notation. Throughout this course, we will be calling this sigma as the notation for our alphabet. So whenever there is a sigma, okay, you understand that sigma is nothing but the alphabet. Okay, so this is sigma is what? The first notation that I used was phi. Okay, and that was the empty set. Sigma is nothing but set of alphabet. Set of alphabet. Okay, so notations are important. Okay, later you might be confused with these small things. So this is alphabet. Now then comes the second part of it. That second part is basically called the rule or the grammatical rules. Okay, second part is rules or the grammatical rules. Okay, before I go to this, let's define one more notation. Okay, one more notation, then we'll come to this rule part. basic unit of the language is alphabet, okay, and now after that what we form in this case is a string, okay. Now the another level is basically called string. What is a string? Now the new term, concatenation, okay, concatenation of alphabets, okay. So very simple thing, alphabet. So concatenation of alphabet. Now your alphabet is A and B, okay, your alphabet is A and B, and now you do this concatenation. How many times? Any number of times. What is the order? In any order, okay. Concatenation of alphabet is basically a string, double A, B, A, okay, double A, B, A, or let's say triple A, or let's say B, B, A, B, okay. So now these are nothing but the concatenation of the alphabet, and that we called is a string. Modulus, let's say this notation A, B, A, okay, length of the string is equal to 4, okay, very obvious, length of the string is 4, okay. So string is what? Nothing but the concatenation of alphabet. What is sigma? Set of alphabet. Phi, set of null set or empty set, okay, empty set or null set, okay. So alphabet, string, okay. Next is set of all string, okay, set of all string, okay. Notation is sigma star, okay, notation is sigma star, okay, sigma star, set of all string, sigma star, okay. I want to write the upper part of it, okay. So sigma star, okay. Now sigma star is the notation for set of all string. Now what is star? I'll come to this. What is a star? Definition of star, that is something related with we call it Kinley closure. We'll come to that, and but right now just to go with this, later definition will come. Sigma star, so set of all string, okay. Now I am maintaining an ordering in this case, okay. I'm maintaining an ordering, that I'm ordering it lengthwise, okay. So symbol, so the first sigma star, what is this? Set of all string. So I'm writing set of all string, okay. Notation epsilon, okay, epsilon. In some, this is epsilon is the most common notation used in the GATE examination, okay. Epsilon is the most common notation for this GATE examination. Sometimes they use lambda, okay, that is also most common notation. So epsilon, what is epsilon? Basic notation, epsilon, single A, length 0, length 1, AB, length 2, double A, AB, BA, BB, triple A, okay, ABA, A, okay, AAB, okay, all right, AAB, ABA, BAA, BAB, okay, BBA and BBB. How many string I can route? I can go on, okay, and that is the most common way of writing a infinite set, okay. So notation, two notations, sigma star. What is sigma star? Sigma star is set of all string, okay, set of all string. And you remember, and you also notice that this is an ordering. Sigma star I have written in a I have not written in a random order, and this is also one of the good practice when you learn about the language, okay, to maintain the ordering. So sigma star written in a certain order, okay. So order is basically this ordering that I have written, okay. Before I this, what is epsilon? Epsilon or lambda, I will use epsilon, okay. Lambda is also common. Epsilon and lambda is a 0 length string, okay, 0 length string, fine, and length of epsilon or length of lambda is equal to 0. Now you guys will be mixing up with phi. Later also you will do this thing, that you will mix up with phi and lambda. That is most common, properties of behavior of students, that they will be mixing phi and lambda. Now phi is a set, okay, and epsilon is a string. Okay, epsilon is a string, phi is a set. Phi is empty set, null set. Epsilon is null string. Okay, epsilon is null string. So this is null string. Both are different object, huh? Remember this thing, null string. And phi, what is phi? Phi is null set. So one is a set, another is a string. Okay, don't mix up these two things. Okay, so epsilon or lambda is a zero length string. These are the terms used in the GATE examination. Whenever lambda or epsilon come, assume that it's null length string. So let this length 0. Okay, ordering. This is length 1. This part is length 2. Okay, this part is length 3. Okay, so first of all, I have written sigma star in lengthwise ordering. And you will do this thing later, that you when write a language, just maintain this lengthwise ordering. Second thing is, I have written ABA before ABA. Okay, okay, I missed one thing. Okay, fine. 1, 2, 3. Okay, fine. ABB. Okay, I missed it here. Okay, so I've written ABA before ABB. Okay, now this is I also maintaining relative ordering. Okay, relative ordering between alphabets. Okay, so I maintain both the thing. In this case, there is a lengthwise ordering and there's relative ordering between alphabet. You will find this concept in dictionary. Okay, when you search an alphabet, A will come. A will come first, then A it will go to A, B. These two properties basically called as lexicographic ordering. Lexicographic ordering. Okay, or dictionary order. So what is a lexicographic ordering? Lengthwise ordering and a relative ordering between alphabets. That A is the first alphabet and B is the second one. So AA will come first, then A, B will come. Okay. So, okay. On that note, let's take a small break. Just recollect what you have done. If you have any doubt, then you can ask. Okay.